So my name, as you can see from the screen, is Chris Saker. I'm one of the lecturers here in the Department of Mathematical Sciences, and I'm quite envious of all the people who are sort of starting or sort of here just with a view to starting their university career, because it's a really wonderful thing to spend 3 years getting to do the subject that you love. I remember sort of enjoying maths at school and then starting my A-levels and being able to spend a much greater proportion of my time doing maths, and this to me was obviously a very good thing. And then I got to go to university and have it be the only subject that I did all day 5 days a week. So this was an absolutely wonderful thing. And you're obviously surrounded by people who are wanting to do the subject themselves. Everyone's there because they've chosen to do it. Your lecturers have chosen to want to spend their lives doing maths as well. So if you enjoy the subject, it's a fantastic environment to be in. So, and what I'm hoping to do today is to give you a little bit of a taste in the sort of 25 minutes or so that I've got of some of the kind of maths that you might get a chance to see at university. I've tried to make it link in a little bit with a subject that some of you may have seen at A-levels. If anyone's doing decision maths, give me a wave. Okay, so if you've done some of D1, some of what I'm saying will sound a little bit familiar, but certainly not all of it. And if you haven't, don't worry, it doesn't disadvantage you at all. I just wanted something that had its roots in A-levels a little bit so you could see what could come from it as we go on into degree level maths. So this is part of a bigger talk, but it's called Combinatorics, which is the area of mathematics, or one of the areas of mathematics that I'm really interested in. And I'm guessing it's a word that people haven't seen before. Again, if you've heard the word combinatorics before, give me a wave. Oh, okay, a couple of people have heard of combinatorics before. So I did say I wouldn't ask anyone to answer any questions, but if you would like to tell me what you think combinatorics is, feel free. If not, don't worry. Silence, okay. So combinatorics is, if you look in different books or web pages, you'll find people describe it in different ways. I've seen it described as the maths of discretely structured objects, the maths of discretely structured or finite countable structures, the maths of patterns, but it's perhaps easiest to think what kinds of questions we ask in combinatorics. So you can ask questions like, if you've got some kind of mathematical structure, how many of them exist of a certain size? Or if we put some constraints in them, can we find the largest or the smallest object, mathematical object, that's got a desired set of properties that we're interested in looking at? So it's to do with counting things and finding how big things are or how small things can be within a particular, with some desired properties on them. You may have seen some combinatorics before. If you've seen questions to do with combinations and permutations, which I'm guessing most people, or certainly most of the prospective students will have done. So if you've had things like 10 athletes running in a race and you wanted to know how many different ways they could finish, first, second, third, fourth, fifth, sixth, all the way down to 10th, then that would be a problem of sort of counting all the possible combinations. You could ask different kinds of questions like how many ways can the top 3 finishers, or how many ways can we get sort of a gold, silver and a bronze place for our race with 10 athletes in it, and how many ways if the order doesn't matter, so I don't care who came first, second or third, I just care about which collection of 3 people finished first, then obviously I'd get different answers to those. So I'm guessing that you may have come across problems like that before and will have been able to answer those kind of questions. Again, I'm not going to ask you how to do it, but it's sort of the roots of the subject, or some of the roots of where the subject can come from. I want to talk about sort of graph theory and a related questions today. So the people who've done D1, graph theory may seem familiar to you. If you haven't, don't worry. What I mean by a graph is not sort of a bar chart or a pie chart or anything like that, or a line graph, but really just some dots on a page somewhere, which we're going to call vertices. And then between our vertices, we're going to join some lines, and we'll call those lines edges. So that would be an example of a graph that had 4 vertices and 1, 2, 3, 4 edges as well. So it's just some dots that I'm drawing lines in between. And we're going to be looking at some of the properties of those. So where did this subject come from seems to be, before I say that, I was going to say that the questions we can ask about graphs include, again, sort of combinatorial questions. How many graphs are there of a certain size that have got a given property? So if I said how many different ways could I draw sort of my edges in if I had 4 vertices, you could work out how many possible graphs there could be with 4 vertices. That would be one kind of question. What types of graphs are there that have certain properties? But where did this subject come from? Well, it came from the 1700s in the Prussian city of Königsberg, which is now a Russian city called Königsberg, and it was situated on the banks of the River Pregel. This is my attempt at recreating the landmass of what's now Königsberg, but was then Königsberg. So you've got 2 banks where the city was situated. You've got an island here, another landmass coming on here, a river running through it, and you've got 1, 2, 3, 4, 5, 6, 7 bridges. When I created this slide myself, the green was a bit better. It's not coming out quite as green as it was on my screen. But anyway, we've got 7 bridges over our river, and the people of Königsberg, being in the 1700s and not having the things to entertain themselves in the evening that we did, would often go out wandering in the evening, go for a walk, enjoy walking around the town and over the bridges, and they wondered if it was possible for them to walk over all of the bridges once without walking over any of the bridges twice. And it was a bit of a local pastime to see whether anyone could do this. You know, you could, for example, say you started up here and end down here perhaps. You could assume that was your walk, even if you then had to go home and cross some other bridges. But was it possible to do a walk that involved crossing all of them once, but none of them twice? And they tried in vain, and no one could seem to find a route that had this desired property. And they were at least smart enough to realise that just because we can't do it doesn't mean it doesn't exist. It might just be that I'm not bright enough to find the answer. Maybe someone cleverer could find the answer. And so they decided to turn to someone who was cleverer, and it was a mathematician. They happened to have living near them a mathematician by the name of Euler, who, if you were to write your sort of top 10 or top 5 lists of mathematicians of all time, he would definitely be a name that featured up there. So they were quite lucky that they had someone incredibly good near them at the time, and they asked him whether he was able to do this. And well, I've had the slide up there for a second now, so does anyone think they've done better than the people of Königsberg? Has anyone been able to find a route? Again, I won't ask you to do it, but if you think you have one, just give me a wave. No one's waving, good, so we're all as stuck as they were. And so the kind of thing that happens is, you know, you walk down here, you walk up here, you walk down here, and then I'm stuck on this bank and I haven't crossed that bridge yet. So no matter how you do it, you seem to get stuck. And what Euler was able to spot, and I'll draw a different picture to represent our bridges, I can draw one node up here for the top bank, one for the bottom bank, one for each of the 2 islands. Then my bridges have got 2 bridges here, one here, 2 here, make that bridge touch, and 1 here. So that's what a graph of my town of Königsberg would look like. And what Euler was able to spot was that if you had a piece of land somewhere and you walked in on it on a bridge, you needed another bridge to walk out on. If you walked in on it on another bridge, you needed another bridge to walk out on. So for every one you came in with, you needed another one to go out on. So we needed things to be even, essentially. We needed an even number of bridges touching our land masses. And he said the only possible place where we don't need this is at the start or the finish. Because at the start, I could just walk out and never come back, or walk in once and walk out again and then never come back, and I could get away with 3. And the same at the end, because I could finish there but not have to have started there. But in general, I wanted to have everything having an even number of bridges or edges touching it, except possibly 2, the start and the finish. So either everything even or all but 2 even. And if we look at this here, we call this the degree of a node is the number of edges touching it. This is 3, this is 3, this is 3, and this is 5. So they're all odd. And so at some point I'm going to get stuck where I've walked in, walked out, walked in, and I've not got an extra bridge to come out on. So you were able to do this really quite easily. If you spotted this little trick, then it wouldn't matter what graph I draw on the board. If I asked you whether it's possible to walk over all the edges once, you wouldn't start by trying to find a route. You just start by counting up all of the edges that were touching each of the nodes, find out the degree of all of the nodes, and if they're all even, there's an answer. If they're all even except 2, then you're going to start at one and finish at the other, and if anything else has happened, it's not going to work. So from this question about people walking over bridges, a new subject of maths was born, and Euler wrote some papers about it, because this is what scientists and mathematicians do. When you've got a new idea, you write it down and you get it published somewhere so that your idea is recorded. And when he was writing about graphs, one of the other things, and one of the first results of graphs that was ever proved, is what's called the handshaking lemma now. And it says that it's, if we write it down sort of mathematically, it says that any finite undirected, so finite just means it doesn't go on forever. Undirected means I can walk over the edges in either direction. I've not got like a one-way street here that ties me into going in one direction. So any finite undirected graph has an even number of vertices of odd degree. Why is that called the handshaking lemma? Because it was often explained to people by saying, imagine that you've got some people at a party or people at a lecture, And if some of the people know each other, they shake hands when they say hello and meet each other, it's always going to be true that the number of people who've shaken hands or who've shook hands with an odd number of people is always even. If you add up sort of all the number of people who've shaken hands with an odd number of people, you're going to get an even number, is what Euler said. And the reason I'm showing this now is to give us sort of our first example of a combinatorial argument that we can use in our talks. And so what we're going to do is we're going to count something twice, and we're going to count it 2 different ways and use the fact that we know the answer's got to be the same both ways. It's like having sort of people sitting in lecture. Now, if I wanted to count how many people, I could count across the rows, or I could count back down the aisles, and hopefully both ways I'd get the same number if I've done it correctly. So it's like a double counting to check yourself. So let's have a look at how we can count this. This is the one slide with an obligatory maths formula on it to make it look like a maths talk. We've got, if we were to count every handshake as involving 2 hands, obviously, because someone's shaking hands to someone else, we're not going to have anyone sort of being smart and shaking with 2 hands. We're just going to assume it's 1 hand involved. Then the total number of hands involved in all of the handshakes has got to be even. Because every time people shake hands, there's 2 hands. So it doesn't matter how many you've got, it's just a multiple of 2. So you've got an even number. So this fairly simple and obvious sounding fact can be represented by a sort of funny looking formula where I'm saying this sigma sign here means add up. So it means add up over all of the vertices, the little vertices, or all of the individual vertices in my set of all of the vertices, capital V, the degree of the vertex, which is the number of edges touching it, or in this case the number of handshakes, has got to be twice the number of edges. So all that's really saying is, if I look at this graph here, I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. It's even. When I've added everything up, I've counted how many times an edge is touching a vertex, or how many hands are involved in handshakes, and I've got an even number because each handshake involves 2 hands, or in graph terms, each edge has got 2 endpoints on it. So that's counting things one way. I've got twice the number of edges, or twice the number of handshakes is the number of hands involved. If I try and count this another way, I can count it by breaking things down into 2 groups. I could count the number of people where the number of handshakes they've made has been even, and I could do the same for the number of people who've had an odd number of handshakes. And if I were to add those 2 things up, I know that I have to get an even number, because I've already done a counting argument that shows that it's twice the number of vertices. Everyone's shaking hands, or every handshake involves 2 hands. So if we count an even number of handshakes, this number has to be even. I know the total has to be even as well, and so the only thing that the number of people who've shaken hands with an odd number of people can be is even 2. Because if this is even, I add something to it and I get something else even, the thing that was left over has got to be even as well. It can't possibly have been odd. So that proves the handshaking lemma. I can write it down a bit more mathematically if I like and say the total degree of a graph is equal to the degree of the vertices of odd degree plus the total degree of the vertices of even degree. I should probably have had total written in at the front of both of those things there. I know the total degree is even. I know that the total degree from the vertices of even degree is even, and so I also know that the total degree from the number of vertices of odd degree is even as well. So that's a nice little sort of argument to show you the kinds of things we do in maths, because obviously one of the things that you'll find differs as you come on, and you may have seen this through your A-levels already, is that there starts to be a bigger emphasis on proving things. It's what separates maths from the other subjects, is that you can sort of write down a sort of categorical argument explaining why something is the way it is, and it's always going to be true. It's never going to change in the future. There's never going to be an experiment that sort of improves on it. If the argument's correct, then it's always going to be correct. And so proving things in maths is a really important sort of concept, and something for us to sort of really spend some time thinking about. And certainly at university you'll get to do that. So that was my first little question. My second is from a slightly different area, and it's something called extremal combinatorics, which is an impressive sounding name, I think. And as the name suggests, it's really about finding extreme cases of things. So it's calculating the smallest or the largest size of a set of objects that have got a certain property. And I want to introduce us to a problem from this by talking about sort of a famous problem to do with something called Ramsey numbers. They're named after a mathematician, Frank Ramsey. He actually died when he was very young, sort of in his 20s, but he did quite a lot in the amount of time that he was around for. And one of the, well, like I say, this is one of the things, there's a whole field of maths called Ramsey theory, which kind of comes out of these kind of ideas. But Ramsey numbers are what we're going to talk about today. So we've had sort of shaking hands at a party. So let's kind of carry on thinking in that vein. So suppose that you're at a party, and there are some other people there, obviously. Now, it's quite likely that some of the people know some of the other people, but that not everybody knows everybody else. If we took this room, for example, there's certainly groups of people here who know each other, and there's other people in the room who you've never met before today, so you'd say that you don't know those people. And that's going to be the case sort of almost whatever room we go into. And so the question is, how many people do we have to have at a party so that it's guaranteed that we've got at least 3 people who all know each other, or at least 3 people who all don't know each other? And the or is important there. I don't want both of these things to happen at the same time. I want to say, if I've got a certain number of people in a room, then I'm 100% guaranteed that either 3 of them all know each other, or somewhere else in the room, there's another set of 3 people who all don't know each other. And I'm going to ask you to think about that in a second, but just to make sure everyone's got the concept right, we're going to make it a little bit easier to start off with. And we're going to think about the 2-person case, where we've got 2 people in a room either knowing each other or not knowing each other. Okay, so if we've got that, then if you think about it for a second, hopefully you can see that we only need 2 people. If there's 2 people in a room, then either you know each other, in which case we've got 2 people who know each other, or you don't know each other, in which case you've got 2 people who don't know each other, and either way our condition is satisfied. So if there's 2 people in a room, they either know each other or they don't know each other. Either way, we're happy. So we can visualize this quite nicely and say that here's case 1, here's my 2 people and they know each other, or here's case 2, here's my 2 people and they don't know each other. So that's the answer to the second case. If I was wanting to write this down, I'd say Ramsey number where I've got 2 people knowing each other or 2 people not knowing each other equals 2. So that's how I'd write it down. And so the question I've asked us is, what's our 3, 3? What's the number that I need, the number of people in a room I need to guarantee to have 3 people knowing each other or 3 people not knowing each other? So let's think about how we could do that. So we've seen how we could draw, if I go back, we've seen how we can draw a graph to help us do this. And I'm going to suggest that it might be a little bit easier if we were to draw, say, a blue line if people knew each other and a green line if they didn't know each other, so you could be sure that you hadn't missed anything out. It's easier to spot a green triangle than it is to spot the absence of a triangle in our graph. So if I picked an example where I had, say, 4 people at a party, and I've got 1, 2, 3, 4, and I've drawn in all of the links, assuming these people either know each other or don't know each other. So these 2 people do know each other, so they've got a blue line. These 2 people do know each other, so they've got a blue line. These 2 know each other. These 2 don't know each other. These 2 don't know each other. And these 2 don't know each other. And so if if R33 was equal to 4, then somewhere in this picture, I would have to have had either a blue triangle or a green triangle. And I don't. And this here isn't a green triangle because there isn't an end point there. It has to be a triangle going between 3. So that's a triangle, 1, 2, 3. But obviously 2 blues and a green. So if you try and find any triangle there, it's going to have blues and greens in the edges. So R33 has got to be bigger than 4. Okay? So my question to you to think about for a moment or two, because you've all probably listened to me for long enough and should try drawing some pictures and seeing if you can do this yourself, is how big do I need my room to be for R33? Is it, we said is it 4 and we said the answer is no, but is it 5, is it 6, is it 7? So parents can have a go at doing this as well. So try drawing yourself 5 dots and then seeing if you can draw, fill in all of the edges so that you've got no triangles that are blue or green. If you think 5 sort of is okay, as in you can find an example you can do that, move up to 6. If you think 6 is okay, move up to 7. We're only going to have a couple of minutes to do this, and then we'll see how everyone's got on. But I wanted to do something that got people involved a little bit. Whilst I can see there's still people puzzling over this, and that's not surprising. It's a bit of a hard concept to get your head around. Can we draw this? Is it possible to do it without finding any triangles? So this is what I'd call a counterexample to R33 being 4, because I have drawn this in, so there's no blue triangle and there's no green triangle. So it's a counterexample. If I'd drawn it in differently, I could have quite happily coloured this line in blue, and then I would have had a blue triangle, but that wouldn't have meant that the answer was 4, because I'd found one example where there was, but the question is there any where there aren't? So if you were playing around with this and you decided that 5 wasn't the answer, then you were along the right track. If you got a little bit further and started looking at 6, and you said 6 was the answer, then very well done. If you've got 6 dots on your page, or 6 nodes, 6 people, and you're drawing in the green or blue relationships between them, then with 6 dots, no matter what you do, you'll always have either a blue triangle or a green triangle. It's impossible not to end up with one. But as in anything with maths, it's one thing for me to say it, it's another thing for me to actually be able to prove it. And so we're going to try and prove that that's always the case. So we've seen that we've seen our 3, 3's got to be bigger than 4. We've seen a counterexample for 4. So I'm going to show you now that it always works for 6, and then give you a counterexample for 5 to show you that it doesn't always work for 5. So to understand this, we need to understand one other concept, which is called the pigeonhole principle, which is really easy to understand. I've got it written up on the board mathematically there, but all it says is if I've got 5 pigeonholes to put things in, and I've got 6 things, then at least one pigeonhole has to have more than one thing in it. Essentially, if the number of objects I've got is bigger than the number of containers I've got to put them in, then at least one of the containers has got to have more than one object in it. And that's what we say down here. We say if we've got m pigeonholes and n objects, then at least one of the pigeonholes where n's bigger than m pigeonholes and n objects where n's bigger than m, then at least one of the pigeonholes has got to have more than one object in it. It's like saying if you had a pile of 5 toys and 3 children and you ask them to pick up all the toys, one of them's going to pick up more than 2 because there's more items than there are children to pick them up. So not a hard concept to understand, but one that still has a name in mathematical circles. So let's look at the following graph. I've called it K6, which is what we call the complete graph on 6 vertices. There's my 6 vertices, and it's complete because I've drawn in every edge possible. And what we're going to do is pick one of the vertices, and I'm going to call that vertex V. Okay? So there's my vertex V. And I'm not going to worry about all of the other vertices too much for now. I'm just going to worry about that one. And if we look at what happens, I've got 2 colours, and I've got 5 edges to colour. So because there's 5 people that V can either know or not know. And so by the pigeonhole principle, one of the colours has got to, or 3 of those edges have got to be either blue, or 3 of them have got to be green. At least 3, I should say. And so I've said, without loss of generality, I'm going to say, let it be blue that's got 3 edges that are blue. So if I go onto this and say, so there's my 3 blue edges. I don't really care about these colours down here, or about these vertices down here, because I've got 3 coming out of here, and that's all I'm interested in. And we're going to look at where those edges are going to. And we're going to say, what happens for these edges? So let's look at them in turn. Well, first of all, I'll look at the relationship between the 2 people on the top. If these 2 people know each other, then I've got a blue edge in here, and I've got a triangle. How about these 2? Well, if these 2 people know each other, I've got a blue edge, so I've got a triangle. And for the last pair, if these 2 people know each other, I've got a blue edge and I've got a triangle. If none of those things have happened, then they're all green, which means I've got a green triangle. So no matter which of those things have got to happen, one of those things has to happen. If either one of these people knows each other, I've got a blue triangle. If none of them knows each other, I've got a green triangle. Either way, I've got 3 people knowing each other or 3 people not knowing each other. In which case, that shows that no matter how I colour in a complete graph on 6 vertices, I've got to have a blue triangle or I've got to have a green triangle. My counterexample that shows that you can draw 5 without a blue or a green triangle is this. So if you look at that, I've got blues going all the way around the edges, green's in the middle, but if you pick any triangle, blue, blue, green, 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 blue. No matter how you do it, you'll have both colours coming up in it. So if you'd searched around for a little while, you might have come up with that picture that showed that you couldn't do it for 5, but 6 was the answer. So, oops. So if we're looking to write a number in here, I'd have 6 in as my answer there. Very nearly done, and then Ed's going to be doing the next talk. But I just wanted to say how big are Ramsey numbers and how hard are they to calculate. Seems to have an extra full stop on that slide there. So we know that R44 is 18. For example, if you were to try and count how many people you have to have in a room, so you've got either 4 people knowing each other or 4 people not knowing each other, it's 18. And that's obviously a bit harder to show than R33 being 6. But how about if we went to 5-5? If I were to ask you how big R55 is, then the answer is no one knows. The question's just too difficult. No one's been able to figure out exactly how big it is, and there's so much computation involved that computers just aren't powerful enough to run through it. If we really worked at it, in fact, a very famous mathematician, Paul Erdős from the last century, when talking about this problem, famously said that if a far more powerful race of aliens landed on our planet and demanded sort of us to provide them with R55 as a sort of measure of our worth in the universe, as it were, then if they gave us a year and all of mankind focused on it, we might just about get there. If they asked us for R66, then we should work on ways of killing them because we were never going to get to it within the time period possible. So really simple sounding questions that can be really hard to state. We know that R55 is between 43 and 49 inclusive, but we don't know exactly where it falls in that. 66 is between 102 and 165. And by the time you get to 1010, all we can say is it's somewhere between about 800 and about 23,500. So suddenly the sort of measures on exactly where these things are become very vague the bigger that we get. So the reason that I put this question in is it shows that there's still a lot of maths out there that people just don't know the answer to. But maybe you guys coming into university, maybe you're going to be the people who make this number a little bit smaller, that bring this down to 47 or bring this up to 45, or maybe even find an answer to it. It's an incredibly big undertaking, but someone will probably do it someday, and why not one of you? So I'm going to finish there, and if anyone's got any quick questions, I'm more than happy to answer them. If not, then we'll move straight on, and Ed can talk. So, sorry, what's that? Yeah, just a lot. Yeah, absolutely. So, while Ed's setting himself up, does anyone have any questions, or? No. Okay. Thank you very much for listening in that case, and I hope that you've enjoyed the day and that you find the next talk interesting.